Problem 42 states, seatbelts and airbags save lives by reducing the forces exerted on the driver and passengers in an automobile collision. Cars are designed with a crumple zone in the front of the car. In the event of an impact, the passenger compartment decelerates over a distance of about 1 meter as the front of the car crumples. An occupant restrained by seatbelts and airbags decelerates with the car. By contrast, an unrestrained occupant keeps moving forward with no loss of speed, according to Newton's first law, until hitting the dashboard or windshield. These are unyielding surfaces, and the unfortunate occupant then decelerates over a distance of only about 5 millimeters. So the airbag's not going to stop him. The seatbelt's not going to stop him. He's going to go 5 millimeters forward. So part A wants to know if a 60-kilogram person is in a head-on collision and the car's speed at impact is 15 meters per second, what's going to be the net force on the person if he or she is wearing a seatbelt and if the airbag deploys? And for B, we want to estimate the net force that ultimately stops the person if they are not restrained for a seatbelt or airbag. So first thing I did is draw out my figure here. I have the car that we're identifying or analyzing, and then here's the other car with the head-on collision. So if our person is restrained with the seatbelt, they are going to go a distance of 1 meter, and unrestrained person is going to go 5 millimeters. So I've identified our variables here. We know our person is 60 kilograms. Our velocity is 15 meters per second. Our restrained occupant is going to have that change in position over 1 meter, and our unrestrained occupant is going to have that change in position over 5 millimeters. So I've converted it to 0.005 meters there. So we're just going to go ahead and use this equation here to find our acceleration because we have all these variables except for A. So plugging in our final velocity, which is 0, because head-on collision, we're totally stopped. So 0 meters per second is our final velocity. Initial velocity we know was 15 meters per second. Square that plus 2a times our restrained person's change in position over 1 meter. So doing the math there, we get our acceleration or deceleration is negative 112.5 meters per second squared. We know that our net force is going to be equal to mass times acceleration, so we can plug in our mass, acceleration, and our net force on that restrained occupant is going to be 6,750 newtons. So moving on to part B, we're going to do the same thing, same numbers, except our change in position is going to be that 0.005 meters. So again, did the math, and I got the acceleration as negative 22,500 meters per second squared. Plug that in to find our net force, and we get our net force as 1,350,000 newtons. So, ouch. Yeah, this shows that seatbelts are clearly going to have less force on us if we have an impact with the car. So, yeah, this ties into what we're learning with Chapter 6 and Chapter 5 of forces and gravity, and reinforces our learning goals for this week for applying full strategy for force and motion problems to problems in single particle dynamics.